Run, piece of shit!
Run, Forrest,
Beep beep. Beep beep.
Run, piece of shit! Run!
Now you wouldn't believe it if I told you.
I can run like the wind blows.
Hey idiot, you're going to trip over your bed. Oh, oops! Wow, holy fuck! I told you so. You're looking like a mess. Ah, no problem. I think we can rebuild you back better.
A man barely alive. Gentlemen, we can rebuild him. We have the technology. We have the capability to make the world's first bionic man. Better than he was before. Better, stronger, faster.
Flat Earth, sex, Flat Earth, sextant. Flat Earth, sextant.
Hey, piece of shit. I heard you dreamed of being a navigator.
The Happy Navigator.
If HO is more, you are toward or closer to it. Just remember ho, mo, to. Ho, more, toward. Ho, mo. Think of the Happy Navigator. Ho, mo, to. Lieutenant Homo To. Homo To. Homo To. The Happy Navigator. Homo.
Laser ring gyros. 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 Laser ring gyros.
Recently, we carried out an experiment to test rotation to the Earth. If the Earth is spinning at one rotation every 24 hours, that means that every hour it has to turn 15 degrees. In today's 21st century navigation systems, they're using what's called a ring laser gyroscope. It is extremely precise. If we could simply get one of these ring laser gyroscopes, we would be able to prove once and for all that there is no rotation to the Earth. One of the people in the community actually purchased one for $20,000.
Did you video record that ring laser for us? Or you show some pictures from Google?
But what we found is when we turned on that gyroscope.
Do you have any recordings of you guys switching on this laser gyro?
We found that we were picking up a drift. A 15-degree-per-hour drift.
Hey Bobby the Liar, did you know only the celestial bodies in the celestial sphere move with that rate? Here, the sun in the celestial sphere. The virtual sun moves exactly 15 degrees in 1 hour.
The apparent motion of the sun is not uniform. For this reason, it would be difficult to construct a clock capable of keeping this irregular time. Therefore, a mean or imaginary sun is used.
Here is 73 azimuth. And then an hour later it's 88 azimuth. And when we look at the observed sun from this location, then it moved only 8 degrees. From 273 to 265.
Now,
Hey Bobby the Liar, did you know only the celestial bodies in the celestial sphere move with that rate?
obviously, we were taken aback by that. Wow, that's kind of a problem, right?
We cannot detect 15 degrees an hour from the observed sun. This app showed the observed sun, so this is what the people see and observe. Let's see how many degrees it moves, roughly. Here at 6, it had an azimuth of 55. And here an azimuth of 64. So that's 9 degrees. From 64 to 71 is 7 degrees. And it moved again 7 degrees in an hour. Let's move from 78 to 85. And that's around the 8 degrees. 85. And again 8 degrees. Oh, and now 10 degrees. You cannot detect the sun going 15 degrees an hour. And on this day, the sun moves with these rates over a full latitude. It's all the same this day. It seems it cannot make a full rotation in 24 hours with this rate. So let's test it for the moon. Only the moon in the celestial sphere do 15 degrees an hour. Let me see. Azimuth. Let's take a rounded number. At 1700. The moon had an azimuth of 116. And an hour later, it had an azimuth of 110. So that's only 6 degrees. And now the speed even dropped 1 degree. And now it's 5 degrees in an hour. And again 5 degrees. So where is this 15 degree an hour motion? And it can even go faster, like 25 degrees in an hour. Azimuth 104 at 12. And now it's 128. So that's like 24 degrees. So we went from 6 degrees an hour to 24 degrees an hour. You see, moron? It happened right in front of your nose. Here, this one do 110 degrees in an hour. From 70 to 323. That's 110 degrees. Only the virtual sun in the celestial sphere and the virtual stars move 15 degrees an hour. Not the observed real suns. Those don't do 15 degrees an hour.
Therefore, a mean or imaginary sun is used. This mean sun is assumed to have a uniform rate of motion with respect to the Earth. As the mean sun is imaginary and the true sun does not have a uniform motion, how then is correct time to be determined in actual practice? And that rate of motion is equal to the average rate of the apparent or true sun during a year.
Maybe you can tell us the location, Bobby. Where did you held this experiment? Because that's kind of important. Because according to globe science, the globe have different rotation speeds. According to science, this is how fast you move on those latitudes. There are many albatross that are thankful for your observation. This Morum seems to be very happy about Bob. Yeah, I can imagine. Bob the liar. So now you're believing a flat earther instead of official science.
So the next thing that we set out to do was to encase the fiber optic gyro in what's called a zero Gauss chamber to see if we could actually shield the energies being generated by the heaven. And we were unsuccessful with that,
Do you have any recordings of that, Bobby?
unfortunately. So the next thing that we're going to try is encasing the entire apparatus in bismuth.
Are you going to make any recordings of that, Bobby?
If everything works well, I'd like to release it at the conference.
Laser ring gyros. 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 The next acceleration it will feel is the rotation of the Earth. And depending on the speed it is feeling, so that acceleration and the speed it notices, it will also start figuring out where it is on the Earth, because the speed will be different if you are down by the equator, where the speed is greater, or if you're close to the pole, where the speed is much, much slower.
Yeah, that's right. Different speeds. Let's put that to the test. We can measure the sunrise between two locations over, let's say, 1000 kilometers, and that gives us some rotation speed according to the globe science. This is 1000 kilometers. And we can measure the sunrise times between the two locations. Sunrise 9:51. And here the sunrise time 10:15. That's about 1 hour and 24 minutes. And that gives us a rotation speed of 714 kilometers an hour. So let's move from December the 21st to June the 21st. There seems to be no angular speed change. Sunrise 1:17. Sunrise 2:42. That's about 1 hour and 24 minutes. 714 kilometers an hour.
So now, knowing the acceleration down towards the center of the Earth and knowing the speed is going forward, it can calculate, all right, I am probably at this latitude.
Because of the rotation speed. Yeah. With other words, if the Earth was spinning with 15 degrees an hour here, then the plane would not know where it is on this globe.
This is quicker when the speed is higher, so the closer you are to the equator, the quicker it will align.
So according to you, piece of shit, the latitude is irrelevant. You're full of shit according to this pilot. It will measure 15 degrees per hour all over the Earth according to you. But it measures not all the other movements. Moron. Here another moron. You have two motions. So why your tiny ring laser don't pick up all those other motions?
If we measure the galaxy's speed relative to cosmic background radiation from the Big Bang, we find it's traveling at an incredible 1.3 million miles an hour. So you're moving on Earth, the Earth is moving around the Sun is moving around the galaxy, and the entire galaxy is moving around the universe at a combined speed of over 1.9 million miles an hour, or 530 miles every second. That means that in the time you've been watching this video, you've traveled over 60,000 miles through space.
So it only picks up the motion of the rotation of the Earth. Imbecile. Did you know, Mr. Fake Pilot, with your 1.1 million subscribers, some ballers think you were wrong?
But also it needs to know where it is longitude-wise, because it can only figure out, right, the speed should put me on this latitude. I don't really know where I am longitude-wise, so that's why we have to put in the current position. And now, since it knows its latitude and longitude and pitch, it will also start feeling, okay, so if I'm at this latitude, I should have this speed. This is a fantastic system. So when we take off, we start flying the aircraft. Obviously, as we're covering distance, we are following the surface of the Earth. That's what we don't want to fly out in space, we want to fly over the surface of the Earth. Now, in relation to an IRS, this means that there will be an angular difference. As we are traveling over the globe, we will actually be, according to the IRS, pitching down a little bit. Now, this is a tiny little drift, but as an aircraft is maybe covering a large portion of the Earth, it will become bigger and bigger as the aircraft starts flying. So the IRSs are set up to compensate for this because it also knows its position. It's fairly easy to compensate for this particular drift.
I see the Earth spinning beneath the plane. Huh.
But there are other drifts as well. Remember how we talked about the fact that the Earth was rotating and that the IRSs could feel that rotational speed? Well, as the aircraft gets airborne, the Earth will still be rotating under it.
Oh yeah, of course, it keeps spinning, it never stops.
And this will cause errors as well when it comes to, for example, the speed. So once again, this is something that needs to be compensated for. And if you're traveling in a north-southerly direction, the Earth will rotate below you as well, and the way that you fly, even though it looks like a straight line over the Earth's surface, since the Earth is constantly rotating, it means that the aircraft is also kind of constantly turning.
Amazing technology! If I take this flight from Amsterdam to Johannesburg, that takes almost 12 hours. Then I will end up almost 180 degrees west. Amsterdam, Johannesburg, almost 12 hours. Between Amsterdam and Johannesburg, we find globe rotation speeds from 1000 to 1660 km an hour. And flying with 800 km per hour, it will never reach its destination, of course. And we can just hover and then land again. And in this direction you will fly more or less backwards.
Because if you're going from A to B on a rotating sphere, you are going to have to constantly kind of follow that rotation with the aircraft. So there are all of these little drifts that needs to be taken into account. Suddenly, and without warning, the GPS system stops working. What kind of backup navigational systems do we have and how do they work? We are heavily reliant on the GPS, the Global Positioning System. But of course, the GPS position is not the only way that we have to navigate. And if the GPS would, for some reason, stop working, we normally have 2 GPS receivers in any given aircraft, so even if one gives up, we still have the other one. But if both of them would stop working, the aircraft would take one step back onto the second best navigational system that we have, which is the Inertial Reference System, the IRS. So, now the third way of navigating is celestial navigation, right? Star navigation. And this was initially used for long-haul aircraft that was flying over oceans. So on the early Boeing 747s, for example, you can still find this star navigation window where the navigational officer would be up there using his sextant and a certain star and the angle it was over the horizon, the time of day. They could actually go into these tables and find out, only based on a couple of different stars and a couple of different angles, almost exactly what their latitude and longitude was.
Ah, the good old Earth curve horizon. So how do you know that's the horizon? Because I see a thick cloud layer. Maybe it's a couple of 100 meters thick and the horizon is way lower, moron.
Now, this is a very good way of navigating, but it's not very precise. It's not something you would want to use, for example, to do an approach.
Yeah, very dangerous with that rotating Earth below you. Better let the computer handle it, right?
Okay, it takes a bit of time, but if you're sitting on a long-haul flight over an ocean, you have plenty of time. And if you do this on regular intervals, it means that you will have a fairly high certainty of where you are as you're crossing the ocean.
So all your systems broke down and you have to rely on celestial navigation. So you make the Earth stop and then you make the stars rotate in the opposite direction, and suddenly you don't have to rely on all those motions anymore. Like the rotation of the Earth, you know, you remember flying with the rotation of the Earth.
Because if you're going from A to B on a rotating sphere, you are going to have to constantly kind of follow that rotation with the aircraft.
They gave this sphere a name, celestial sphere. From Earth, it appears to move from east to west. One complete rotation every 24 hours. Using ancient man's concept that the Earth is stationary, we imagine the celestial bodies on the celestial sphere to rotate from east to west. In effect, we are creating a new reference system with your position at the center.
Yeah, from anywhere on the globe. You're going to be straight up and create a flat level plane and put yourself in the center.
We have used the sun as an example, but the apparent motion is common to all celestial bodies. Their hour circles are constantly rotating from east to west.
It is convenient to assume that we are at the center of a great sphere of infinite radius, and that the heavenly bodies move about us on this celestial sphere.
So how do you account for that globe rotation when you do celestial navigation from an airplane? It seems in the old days they never account for that rotation.
However, the advance in airplane design, bringing forth fast aircraft capable of sustained flight for great distances over large bodies of water as well as over land, has prompted the Army to adapt to aviation the navigational methods of the mariner, namely dead reckoning and celestial navigation, and to devise instruments to enable a pilot to accurately fly a given course. Among other things, student navigators are taught to fly entirely by instruments, to determine drift and ground speed by specially constructed instruments, and to determine position by sighting on celestial bodies with the bubble sextant.
Oh, latitude parallel flying without taking rotation and the tilt in account. Oh, MacArthur chart flying. Oh, a flat map and you draw straight lines. Yeah. I don't see fancy tools to calculate the rotation speed below you and then figure out where you are. Huh. Oh, air restrictions. Maybe I see fancy tools here. Let me see. Dead reckoning. Impossible. With the spinning globe below you. Air practice with the sextant. Huh, let me see. Oh, you take off your parachute. Yeah, that's a good idea. Otherwise, you fit not in that tiny hole. Put on a coat, because it's very cold outside. Must be cold up there. Put on your coat. Oh, now you're suddenly wearing your coat. Yeah, that's enough. Now go inside and take off your coat, idiot. Well. Who do we have here? Magoon. What did you do? Sex offender. Did you rape a 6-foot woman? Piece of shit. So this must be fake hair then. Did the police take off your wig? Piece of shit. So you're this 4-foot tall sex offender. I wonder how big your Johnson is. 4 millimeter. Oh, it's not called Mr. Johnson. It's called Mr. Micro.
Always look on the bright side of life. Life's a piece of shit when you look at it. Life's a laugh and death's a joke, it's true. You'll see it's all a show, keep them laughing as you go. Just remember that the last laugh is on you. And always look on the bright side of life. Life's a piece of shit when you look at it.
But since we are people of science, we know about all of these things. Laser ring gyros.